would like to express my gratitude towards Data Science Festival organizers for having me over. Today, I will be talking about propensity measurement using PU bagging. And here by propensity, we mean the likelihood of a given customer to shop online on the retailer's e-commerce portal. And PU bagging is, PU here stands for Positive-Unlabelled, and it's a semi-supervised binary classification technique, which is trained on a data set where only positive instances are known and rest are unlabeled/unknown. So they can be either positive or negative, and PU learning thereby enables tagging of those unlabeled instances into positive and negative. How it happens, I will illustrate in the subsequent slides. So the agenda for today is I will start with an introduction to my organization, then move on to the problem statement at hand, and followed by the typical traditional solutions to it and why they are not recommended. So that's the important part, which will lead us to build a case for the alternate solution framework, that is PU bagging. And finally, we will cover the deployed solution pipeline, starting with feature engineering, then move on to working of PU bagging and the resultant segmentation, and conclude with the validation of those identified segments. So Dhanambi, Dhanambi is a customer data science company with global presence. We have helped hundreds of retailers and CPG brands perfect the art of shopping and truly become customer first using high quality data science, which in turn is based on the analysis of shopping behavior of more than 770 million customers, active customers. So we can imagine that's roughly 10% of world population. For CPG clients, we provide solutions in various areas, such as customer insights, assortment, promotions, and media. And for retailers, we provide solutions into merchandising, marketing, operations to create customer loyalty, which drives efficiency and increases sales. As part of applied data science team, I myself have supported retailers in pricing and promotion optimization, assortment review, campaign management, demand forecasting, and obviously online channel propensity measurement, about which I will be talking in detail in today's session. So jumping to the problem statement. So our client is a leading health and beauty retailer with offerings into categories like personal care, dermocosmetics, makeup, perfumes, baby care, female hygiene, and so on. And more than 90% of its customers are female. The retailer launched its e-commerce store in 2019. Initially, the online transactions only increased nominally. But as we can imagine, they jumped during the COVID lockdowns. So now the retailer is targeting to widen its online presence as it's associated with higher sales and more customer interaction. And consequently, the data science mandate in this objective is to score each and every pure offline customer's probability of shopping online. And by online here, we mean the retailer's e-commerce portal. And once we have scored each and every customer by this probability, we will segment those customers into two groups. First group will be the potential, which can be nudged to shop online with minimal acquisition cost. And the unlikely group will be that which can be ignored during the target campaign. So with this problem statement, one of the traditional solution is a possible knee-jerk solution is that we like here we see the list of here is a sample of customers. So ones are those which are the existing omni-channel customers, while zeros are those customers who have never made a purchase online. So the traditional approach would be one of them would be the supervised learning. We do a simple train test split. We create a model on this train set, optimize it, improve it. And once that we have that optimized model, we apply this model on the feature vector of each and every pure offline customer to compute their probability of shopping online. But this framework is flawed because this framework assumes that in the train sample, for example, these zeros, which we are taking as zeros, they will remain the offline shoppers in future too. But we don't know about that. So they can shop on online in coming days. And also there could be a chance that they are already shopping online on other channels. So within these so-called negatives, there is a chance that they could be the potential online channel customers. So this framework is flawed and counter-objective, as it assumes the negative instances of training set will continue to remain the offline shopper in future too. And also here, I would like to emphasize that let's say we create a perfect model using this train test split. And by perfect model, I mean 100% accuracy. If we have that perfect model and we apply that perfect model on, let's say, this customer, which is supposedly a pure offline customer in train set, so it would assign a probability 0 to this customer. So we won't be able to get any, we won't be able to unravel any probability among existing offline shoppers. And this is a bit paradoxical in the light that we will be creating a perfect binary classification model. So that is why this approach is flawed and counter-objective. Second possible solution to the problem statement at hand is that we do clustering. But it would only work if we are able to prepare clusters such as which are appearing in figure A. And here, like the nodes which are dark in color, those are the customers which are presently online shoppers. So if we get a cluster like this in which all the existing shoppers on existing online shoppers fall in one cluster, then probably we can assume that the remainder of those customers in this same cluster can be taken as potential. But that did not happen, and the actual outcome was the existing online shoppers were distributed across multiple clusters. So its success is rare and circumstantial. So to reiterate, in our problem statement, supervised learning is flawed and counter-objective, while the success of unsupervised learning is rare and circumstantial. So, which leads us to create a case for semi-supervised learning. So here the premise is, instead of taking those customers who have never shopped online as negatives, as zeros, they should be taken as unlabeled. And now this transforms into a positive unlabeled bagging exercise. So we have gone from the supervised framework to the semi-supervised framework, where we are taking each of those customers who have never shopped online as unlabeled, not as negatives. And the solution pipeline is a typical solution pipeline. We do feature engineering, then we do propensity measurement using PO bagging, which I would illustrate. And finally, we conclude by validation of the resultant segments. So starting with feature engineering, we looked at 3 customer dimensions. First was the shopping behavior in last 12 months. So how many visits have each customer made? What is the volume, which is the summation of all the units bought by a given customer? How many of those visits were attributed to promotion, which is the promo share? How many days have passed since the last purchase, which captures the recency effect? And what is the mean gap between their purchases? So how many days on average have passed between their 2 consecutive visits? Secondly, we looked at customer demographics. Here we looked at 3 features. First was gender, second was age, and third was city population. Not the city name, we took the city population size. So that serves as the proxy for whether a city is metropolitan or a tier 2 city. So higher the population, it is a de facto metropolitan. And taking city population as a feature that removes, instead of the city names, that removes the need for one hot encoding. So we have a more readable feature, more interpretable feature. Third dimension was category preferences. So as I mentioned, the retailer is into face care, dermocosmetics, female hygiene, fragrances, and so on. So to calculate category preferences, we did the average of spend distribution as well as volume distributions for each and every category. So let's say if customer spends 2% of their spend on fragrances, and in terms of volume, only 0.5% of volume is attributed to fragrances, then the average would be average of 2 and 0.5. So 1.25%. So that is what we mean by average of spend distribution and volume distribution. The rationale behind it is some categories are volume heavy products, which is like they have low price per unit, like face wipes. So, and some are spend heavy products like fragrances. So they are bought in less quantity, but their price per unit is very high. So common practice at Dhanambi is to do a simple average of spend share and volume share. So that effect of either spend heavy or volume heavy does not distort the resultant feature. And finally, the target variable is for those shoppers who have shopped previously online, we take them as one. So those are positive. And remaining are treated as unlabeled, those who have never shopped online. So how does PU bagging works? So to explain that, let's say we have these 15 customers. So these 15 customers are customer 1, customer 2, customer 3, and so on till customer 15. So their ID number is in those notes. And those which are highlighted in green, these are customers who have shopped online in previous 12 months. And remaining customers which are highlighted in gray from 4 to 15, they have never shopped online in previous 12 months. So what we do on this unknown, unlabeled customers is we create one in bag and one out of bag. So let's say we sample customers 4 to 5 and put them in a bag. Let's imagine a bag, placeholder bag, and we put all those unlabeled samples in the bag. And remaining unlabeled customers are kept, which are customers 13, 14, and 15, are kept out of bag. So those are out of bag unlabeled samples. Next step is we create bag of models, and that is what we refer to here as bagging. So the bag of model is from those in-bag unlabeled samples, we randomly and iteratively sample some of those customers. So let's say in first model, which goes into the bag, customers 4, 5, 6 are sampled. While this classifier 1 is being trained, only during this period, these customers are become transient negatives, but just for sole purpose of building this classifier. And here idea is also to sample equal number of so the number of online customers while a model is being trained should be same as the number of unlabeled, which transiently become negative while that classifier is being trained. So here it is class balance. So while classifier 1 is being trained, it will have equal number of, here we have 3 online customers and equal number of unlabeled samples, which are transiently negative. So this is how we train classifier 1. Similarly, we train a classifier 2. Here the random sampling of in-bag sample changes from 4, 5, 6, now it is 7, 8, 9. And similarly, the third model which goes into bag is 10, 11, 12. But it's just for illustration, I've only shown 3 classifiers. Theoretically speaking, from these 12 customers, 9 customers, from customers 4 to 12, we can sample 84 unique combination of customers. So we can create a bag which creates such 84 samples, 84 models, sorry. So, and here I just want to emphasize the fact that right now, no model has seen these out of whack samples, which is customer 13, 14, and 15. So once we have this bag prepared of all the classifiers, classifier 1, 2, 3, what we do is we compute the propensity. And propensity is computed by we predict with each of those classifiers on each of those out of bag unlabeled samples. We get probability by each of those classifier for each of those out of bag sample. And finally, we do a simple row-wise average of that probability. And against each out of that sample, we will get a resultant probability. And that probability will range between 0 and 1, obviously. Here we have taken on an arbitrary threshold of 0.5. So if a probability is greater than 0.5, then it is labeled potential. And if it is less than or equal to, it is labeled unlikely. So this entire illustration, though this had 3 models, but this was only one iteration where we were in that iteration, the responsibility was to label and assign probability to these customers, which were kept out of that 13, 14, and 15. But in subsequent iterations, different customers will be kept out of that. So then, so that we can get a independent probability for each and every unlabeled sample. So in iteration 2, customers 4, 5, 6 will be kept out of that. And in the end, we will get a probability for these customers as well, 4, 5, 6. In iteration 3, customers 7, 8, 9 will be kept out of that. And we will get a probability for these customers as well. And so on till iteration 9, till the point we assign a probability of to each and every unlabeled sample independently. By independently, we mean that that particular instance was not part of the training process. And finally, output will be such that of all those unlabeled samples, some will be tagged as potential. So here, just for purpose of illustration, customers 6, 7, 11, and 14 have been tagged potential, and remaining customers have been tagged unlikely. So we have done the segmentation into potential and unlikely. But how do we conclude and state that this segmentation is useful and it is likely like what we did was good or not? So how do we define that? So that is the challenging part, because uh, in the typical traditional supervised learning, we have the ground truth available in the test set against which we can match and create a confusion matrix, draw the ROC curves, and uh, evaluate whether model is good or bad. But here we don't have the values pertaining to ground truth. So the evaluation cannot be definitive. It can only be indicative. And the indicative evaluation is kind of triangulation of 3 evaluation processes. So first is we establish similarity between the potential and existing groups. And so all those customers who have been tagged as potential online shoppers, are they indeed similar to the existing groups or not? So that is the first indicative evaluation. Second is a retrospective evaluation of PO bagging. So we do a out of time evaluation whether this technique is likely to stand test of time or not. And finally, we do the profiling of the potential group vis-a-vis the unlikely group, whether it whether it makes sense or not, whether it passes the sense check by the market leads. So we do these 3 checks to validate the segmentation. Again, I want to emphasize this validation is only indicative. It cannot be definitive because we don't have the ground truth available. We don't know whether the customers which we are tagging potential, whether they will shop online in future or not. At this time, we don't know. So how do we establish similarity between the potential and existing omni-channel customers. So building on that illustration, we were able to tag customers 6, 7, 11, 14 as potential. So what we do is we take them all those customers as positive and remaining customers are negative. And we do a good old 50% train test split on this and build a classifier, a binary classifier on the train set. And we evaluate the accuracy on both train set and the test set, both accuracy and recall. Here we are getting a respectable value, which is like more than 95% accuracy and more than 90% recall. So this indicates that the customers which we have tagged as potential, it's highly likely they are similar to the existing customers. Second mode of validation is a retrospective evaluation. So we apply the same tube bagging technique, but only on features which are built going back 32 weeks, 52 weeks, and 72 weeks. And on those feature vectors, we tag customers as potential and unlikely. And once we have this potential and unlikely at T minus 32, T minus 52, and T minus 72, we map and cross-check, cross-reference them again, existing and offline only customers, which is our time T now. And against that also we do a similar accuracy and recall check. And here also, it's not as high as 90% or 95%. But going back 32 weeks also, we can say that it's highly likely that we are able to unravel the potential using this technique. Finally, is the profiling of the potential group. So here we compare how they perform of some KPIs. The comparison is between, again, potential and unlikely omni-channel customers. And first, we observe the shopping behavior. So the potential customers are those who have made fewer visits, but purchase more on each visit, which is very typical online shopping behavior, that we tend to buy more and more in one visit. So, and also they were recently engaged with the retailer. So they have made a purchase in last 2 months. In demographic, they are more likely to be on the younger side. They are more likely to be under age of 30 and be from one of the top 10 cities of that particular country. So this also falls in line with market expectation that younger customers are more likely to use the online channel and also are more likely to be from the metropolitan city. Finally, the category preferences. So the potential group had higher propensity to buy products like natural spa, dermo and pharma, makeup, and face care, and had lower propensity to buy products like fragrances, which are experiential products. Like these are the products customers like to buy in the brick and mortar store after testing and trying. So that also was observed in this. Finally, so the outcome was that at the start, 11% of the shoppers were existing e-commerce shoppers and remaining were non-e-commerce shoppers. And among these non-e-commerce shoppers, we were able to identify further 17% as potential. So here also we see a nice pyramid, if you can imagine that 11% of existing at top, followed by 17% of potential, and 54% as unlikely. And some were kept as unclassified because of lower number of visits. So here also it passes some sort of the sense check. And the outcome was that with the right marketing strategy, a retailer has the potential to almost triple its omni-channel customer base. Yes. So, and to conclude, this technique can also be applied for, let's say, product or category recommendation, promotion targeting. So any exercise in which involves to like which involves the need to measure the propensity to whether to buy a new product, uh, use new service, or whether a propensity to whether given promotion can be used by a given customer or not. So wherever there is a need for propensity measurement, we can indeed use PU battle. That's all from my side.